Hello. I was looking at this week's lab journal for week 4, and it's pretty challenging. So I thought I would take a few minutes and guide you through it, hopefully giving you all the information you need to solve the problems. So let's open up the journal here. Okay. So this part I don't think needs any explanation anymore. You've already done this. Um, so do it for the 3 labs you have this week: Newton's laws of motion, uh, safety in motorsports, and law of universal gravitation. So, there's a question here about a couple people on a planet. They want to leave the planet and enter orbit so that the mothership can rendezvous with them. So they find some things just by being clever and making observations. So they estimate the radius of the planet to be 7,582 kilometers. And then Janice is very clever. She builds a pendulum with a length of zero point 0.7 meters, and there's a weight at the end. And when she swings the pendulum, it swings with a period of 1.54 seconds. So the first question is, what's the acceleration due to gravity? Now, the acceleration due to gravity affects the period of the pendulum. Now, that's a little tricky. So I'm going to show you where to find that information. So go back to your lab and go to the law of gravitation lab. And then go to the theory section and look down here somewhere. And you see simple pendulum. Click on that. Well, it shows you a picture of a pendulum, but not much else. So then click on the article on the derivation of the period of the pendulum and gravitational acceleration. So right here is what we need. This expresses the gravitational acceleration in terms of the length of the pendulum and the period. So you're going to find the answer by using the formula that I just showed you. G equals 4 pi squared L over T squared. Okay, there's L, and the period is right here, 1.54 seconds. Okay, just plug those numbers into this formula, and you will get the acceleration of gravity on the surface of the planet. All right, then they have to know something else. They have to know the mass of their ship because they're going to launch the ship into space, and they need to know how much thrust they have to apply. So they need to know the mass of the ship. Well, they use a version of the Cavendish experiment. So you can read about that in chapter 6, but I'm going to save you the trouble and kind of set this problem up. So I'm going to make a free body diagram, and I'm going to um, just make a free body diagram for the pendulum bob. So the forces on the pendulum bob are given by the tension from the string, the force of gravity from the planet, okay, and then the force of gravity between the spaceship and the pendulum bob. I'm going to draw in some dashed lines. And these are the components of the tension vector. Now, if I look at the angles, by similar angles, this angle here is also theta. See, I'm looking at this, and this angle here is theta, but that angle here is also theta. And that's what I'm showing in this diagram. This component up here, using some trig, basic trig, is t times the sine of the angle. And this side, let me move this label over. So FG is here. This side is t cosine theta. Now, if you look at this diagram, there's only one component of force in the vertical direction to balance gravity. So I can see from here that t cosine theta equals mg, right? Because this pendulum is stable. It's in equilibrium. So all forces have to add up to zero. And there's also only one force in the horizontal direction that can balance the force of gravitational attraction between the rocket and the pendulum bob. And that's t sine theta. And that's equal to, from Newton's law of gravitation, uh, gravitational constant times the mass of the rocket times the mass of the pendulum bob. Okay, so the mass of the rocket I'm going to call m, capital M for this, all right? And r is the distance between them, which in this case is 5 meters, right? It's shown right there. All right, let's now, I have that, put a box around it. Now over here, I'm going to take the ratio of those two formulas, t sine theta over t cosine theta equals, well, if you remember any trig, that tension cancels out, by the way, and you have sine over cosine. That's just a tangent of the angle. And then I'm going to have gmm over r squared, gmm over r squared, divided by mg. So I'm actually dividing the bottom formula by the top formula. And that little m cancels out there. So now I have gm over r squared g. And I'm trying to solve for m. So it's just simple algebra. I have that the mass of the rocket is r squared g tangent of theta divided by the gravitational constant. Okay? This is the formula you need to find the rocket's mass. Okay, remember, this g is not the acceleration of gravity on Earth, which is 9.8 meters per second squared. It's the acceleration of gravity that you calculated up here. Okay. We're finding the acceleration of gravity for Gliese 832. All right. So I want to be clear on that. All right. Now, to achieve orbit, they have to find out how fast they have to go to be in orbit, which depends on the altitude they wish to achieve. So Kyle is confident that an altitude of 10,000 kilometers will be enough for them to be found by the mothership. So how are you going to find the acceleration of gravity at that altitude? I'm going to have to get the whiteboard. Okay. So we're going to use Newton's second law of motion, which says that force equals ma. Now in this case, the force is the force of gravity. So it's g, mass of the planet, times the mass of the whatever it is that's in orbit, divided by the radius of the orbit squared. Well, see, the mass of the thing that's in orbit is on both sides of the equation, so that goes away. The acceleration of gravity is just gm over r squared. Now, let's say we're looking at two different radii of orbit. You have, okay, you can be on the planet, and that has an acceleration of gravity g1, let's call it. And then you go to some other distance, so that's r1, I'll say, and then this is r2. Okay, and the acceleration of gravity there is g2. So let's do in terms of those numbers. The planet's mass doesn't change, so we have g1 equals r1 squared. Now we already found that. That's the g that we found. g2 is g, to stabilize my screen, over r2 squared. Now we can take a ratio again. Just divide the bottom by the top. We have g2 over g1 equals, well, I'll just write it all out here, gm over r2 squared over gm over r1 squared. The g's cancel, the m's cancel, you get the r1 squared on top, so that equals r1 squared over r2 squared. So now I have a simple formula. If I know what g1 is, I can find out what any other value of g is at any altitude. So g2 equals g1 times r1 squared over r2 squared. Okay, let's go back here. That's the formula we want. Okay, so all you do is, if you calculated the correct value of g here, and you know what the radius of the planet is, right? It's this, but remember, convert to meters. Everything's in meters. And this other radius is the orbital radius, which corresponds to an altitude of 10,000, which means you have to add 10,000 to the radius of the planet, okay? Now, what's the velocity to find a standard orbit? Okay, let's go back to the whiteboard. All right, so we want to find out the speed necessary to orbit the planet at an altitude equal to the radius plus 10,000 kilometers, right? Convert it into meters, though. Okay, the radius of the orbit we'll just call r right now. Now, when something's moving in a circle, you can check this in chapter 6. There's a centripetal acceleration, a sub c, and which is equal to v squared over r. But what provides that centripetal acceleration? It's gravity. So the centripetal acceleration is equal to the acceleration you just found. The acceleration due to gravity at that radius. I called it a minute ago, I called it G2, right? So let's just keep that notation, right? It's this G2 right here. So V is just the square root of R G2, where R is the radius of the orbit. Okay. Now they want to determine the thrust needed to propel their rocket into orbit safely. And they don't want to be harmed, of course. And they know, I guess they're, in good physical shape, and they can handle 3 times their earthly weight um, as they accelerate into orbit. So, what's the maximum acceleration they can endure, right? Let's go back to the whiteboard. Let's make a free body diagram of a person. I'm just going to represent a person by circle. Okay. Uh, there's an upward force. I'll just call it the normal force. That pushes the person up. And there's a downward force, which is a person's weight, which is mg. So the normal force minus mg has to equal the mass of the person. It's the net force, right? This is the net force here. And by Newton's second law, that's the acceleration. If I want that to be the maximum acceleration, then this has to be 3 times m, the mass of the person, times 9.8 meters per second squared, right? That would be 3 times the earthly weight. So I'm going to write 3 times m times 9.8 meters per second squared minus mg, which is the g you found earlier at the surface of the planet, is m a max. A max is what you want to find. Well, this is the same mass all through, so that cancels out. So a max is equal to 3 times 9.8 meters per second squared minus g, where g is the acceleration of gravity on the planet. That's what you found when answering the first problem, problem number 1. Okay, so that is what you need to calculate the maximum acceleration. So a max is 3 times 9.8 minus g, where g, again, is this g here that you calculated in problem 1. Let's make sure you get these straight. So how much thrust must they dial in to achieve this maximum acceleration? I don't know what that is. It should be, maximum acceleration target. Now we want to know how much thrust is needed to propel the rocket up with that acceleration. So we have to go back to the whiteboard. Let's make a free body diagram of the rocket. Here's our rocket. And the forces acting on the rocket are the thrust. That's what we want to find. And force of gravity, mg. That's the g due to the planet's gravity. Okay, remember, it's not 9.8. This is the acceleration that you found problem 1. Right. And the rocket accelerates upwards with acceleration equal to a max, which we found. So the equation, Newton's second law applied to this problem would be T minus mg equals mass times the acceleration. So the thrust is just going to be m times g plus a max. Okay, where this is the mass of the rocket. So I'll write that on the problem. All right, now we want to find out how far in kilometers they would have traveled before reaching the speed necessary to achieve orbit. So we're going to use one of the kinematic equations that relate distance traveled to the change of velocity and the acceleration. So that looks like this, if you recall. Twice the acceleration, which is a max, which we found before, is equal times the distance traveled. That's just the distance. Equals the final velocity squared minus the initial velocity squared. Well, the rocket starts from rest, so initial velocity squared is 0. So we can solve for s minus s0, which is the distance traveled. That's what we want to find. Okay, this next one is just a question trying to make sense of the distance traveled. You'll find out, hopefully, if you did everything right, the distance traveled is greater than the orbital altitude. But does that mean that you're going to go to a higher altitude than the orbital altitude? Just think about it and answer it uh, as best you can. Now, a thing to be aware of is that the distance you get here, if you plug in all the right numbers, is going to be in meters. You have to convert to kilometers, remember. Take the distance in meters, divide it by 1,000, that gives you kilometers. Okay, to save some time, I went ahead and wrote in the formulas here. So, how long after launch will it take to reach orbit? Well, I just have the kinematic equation for velocity. And again, since the initial velocity is 0, we can solve for the time from that. It's just the final velocity or orbital velocity divided by the acceleration. Okay, that gives you the time. That would be the time in seconds. After you reach orbit, you have to wait for the mothership to come along, and that happens in 12.7 hours. So how many orbits did the two astronauts complete before meeting the mothership? Well, we first want to figure out the time it took for an orbit. So we remember that the speed is distance over time. The distance for one orbit is 2 pi times radius. It's just a circle. We're assuming circular orbits. That distance divided by the period, t, is the speed, right? All right, so solve for t. T is 2 pi r over v. That would be in seconds. The number of orbits is the time divided by the time per orbit. But we have to get everything in the right units. So if I know I'm waiting around for 12.7 hours, I can convert that to seconds by multiplying it by the number of seconds per hour, which is 3,600 seconds. And then if I divide by the time per orbit, I get the number of orbits. Okay, so that's all spelled out for you there.